वेलकम टू फिजिक्स मेड इजी चैनल। आज हम जो प्रॉब्लम स्टार्ट करने जा रहे हैं, वी आर गोइंग टू सॉल्व एनसीईआरटी एक्सरसाइजेज ऑन वेव ऑप्टिक्स एंड वी विल प्रोवाइड कंप्लीट सॉल्यूशंस टू एनसीईआरटी एक्सरसाइजेज। एंड नाउ द फर्स्ट प्रॉब्लम, मोनोक्रोमैटिक लाइट ऑफ वेवलेंथ 589 nanometers, this is the wavelength of monochromatic light, is incident from air on a water surface. What are the wavelength and frequency and speed of reflected and refracted light? Refractive index mu is given 1.33. Now, the very first thing that you should notice in the process of reflection, wavelength, frequency and speed remains the same. Remember this thing. In the process of reflection, this wavelength, frequency and speed, all these remain the same. So the speed of light will be c, that is 3 into 10 raised to power 8, and the wavelength again will be 589 nanometers. And if we have to calculate its frequency, then the formula is very much simple. C is equal to nu lambda, and he is using C is equal to F lambda. Now lambda is given and C is also known. We can calculate F is equal to C by lambda. Now C is 3 into 10 raised to power 8 divided by lambda. This is 5, 8, 9, 10 raised to power minus 9. From here we shall be making calculations and it will come out to be 5.09 into 10 raised to power 14 hertz. So now we have followed one dictum, one main principle in solving this whole problem, and that was in the process of reflection, wavelength of light, everything, wavelength, frequency and speed of the incident light remains constant. So its speed is given, its wavelength is given, frequency we have calculated from the formula C is equal to F lambda. Let us proceed to the next problem. Now here lies the difference. In the process of refraction, what remains constant is frequency. F remains constant in the process of refraction. In the process of refraction, all of us know that F remains constant. F is constant. In refraction process, I will write here, in refraction, frequency remains constant, and I have just calculated frequency to be 5.09 into 10 raised to power 14 hertz. And for that, we also know refractive index of water with respect to air is equal to velocity of light in air divided by velocity of light in water. Now refractive index is given to us 1.3 and we are interested in calculating V. So V is equal to C divided by 1.33, and if now I fill the values, this is 10 raised to power 8 divided by 1.33 and it come out to be 2.26 into 10 raised to power 8 meter per second. And now from here we can calculate lambda. Lambda we can calculate. Lambda is equal to V by F. Fill the value of V, 3 into 10 raised to power 9, and then fill the value of frequency, 5.09 into 10 raised to power 14, and then we will get the value of lambda, and lambda has been found to be 444 nanometers. Now The next NCERT questions, and let me remind you very clearly that the questions asked in NEET, JEE Main or in JEE Advanced, their base is NCERT. For JEE Main, just solve NCERT problem or NCERT exemplar thoroughly and pick up the concepts clearly. You don't need to bother about any other book in the market. Just bother any other book only for practice and not for building the basics. And now the next problem. I will again change the color. We often change the colors. Now, what is the shape of the wavefront in each of the following case? Light diverging from a point source. Now, the wavefront is spherical in this case. This is basically a theory question. The wavefront in this case is spherical, light emerging out of convex lens when a point source is placed at focus. Now, if you place a point source at focus, let me draw this diagram. So this is the principal axis, and if I take this as a lens, if this is the focus of the lens, and all the rays placed at focus after refraction, they become parallel and they meet at infinity. So there is slight so they become parallel after refraction from here. They will become parallel and they will meet at infinity. And parallel rays, they give rise to plane wavefront. Plane wavefront. So basically it's a question directly from theory. Light emerging out of convex lens. When a point source is placed as focus, this is convex lens and it will become parallel. And the wavefront corresponding to parallel rays is plane wavefront. And the first question was light diverging from the point source. When light diverges from the point source, then we get spherical wavefronts. It's quite easy. We get spherical wavefront. I will show you the corresponding diagrams. So this is the diagram. So this is light diverging out of a point source. We get spherical wavefronts. When light converges to a point source, we again have spherical wavefronts. Now these are the parallel rays. Parallel rays give birth to plane wavefront. And let me check the next problem. The portion of the wavefront of the light from a distant star intercepted by Earth. Now when star is at a very large distance, so all the wavefronts, whether spherical or cylindrical wavefront, when they come from a large distance, they become plane wavefront. Note this point. So I think all these points, they are quite clear. So they will become all, whether spherical or cylindrical plane wavefront, at a larger distance they become plane wavefront. Light will be a parallel beam after passing through convex lens. Spherical wavefront, all particles vibrating in the same phase lies on the same sphere. So I think in C part it is again plane wavefront. In B part was light. You place the source of light at focus. After refraction you get parallel beam of light and thereby obtain plane wavefront, and light diverging from a point source is spherical. And now let us come to problem number 3. NCERT third problem. What this says, refractive index of glass is 1.5. What is the speed of light? Simple. It's a very simple question. In fact, we have got this formula. Mu is equal to C by V, or V is equal to C by mu. So now V is 3 into 10 raised to power 8. Mu is 1.5. So V is 2 into 10 raised to power 8 meter per second. Is the speed of light in glass independent of the color of light? No. If not, which of the two colors red and violet travel slower in glass prism? Now speed in light, how does it depend? Leave it. Remember this formula. Mu is inversely proportional to speed in medium. And mu, according to Cauchy's formula, is inversely proportional to a function of lambda square. So it means if mu is inversely proportional to V and mu is inversely proportional to, you can say, lambda square according to Cauchy's formula, we can say that V is proportional to lambda or lambda is proportional to V, whatever may be the case. Now, we know that wavelength of red color is larger than wavelength of violet color. It means refractive index is inversely proportional to this. It means refractive index of violet color is greater than refractive index for red color, but it is inversely to velocity. Refractive index is inversely to velocity. Now, this means that in case of velocity, things will get reversed. V red will be larger than V violet because lambda is directly proportional to velocity. Larger the wavelength, larger the velocity, larger will be the wavelength, or inversely, larger the wavelength, larger will be the velocity. Now let us see what he has asked. Is the speed of light in glass independent of the color of light? No. If not, which of the two colors, red or violet, travel slower in glass prism? So red will travel slower? No. Violet will travel slower. Violet travels slower. Next is, in Young's double slit experiment, the slits are separated by a distance 0.28 mm. Note down the distance between the slits is in mm and the distance of the screen is in meters. The distance between the central bright fringe and the fourth bright fringe is given to be 1.2 centimeter. Determine the wavelength of light. Now let us have first a look at the diagram. Now the diagram corresponding to Young's double slit experiment is something that one should keep always in one's mind, and this is that diagram. This is the diagram. Now this is the distance between the sources. Distance between the sources can be represented by small d or a. This is very small. This is in millimeters. And this is the distance of the screen. This is in meters. For example, 1.4 meter. Now let us come directly to the formula. This distance d, as I have just represented, 28. This is 28 mm. This is 1.4 meter. This is millimeters. Means 1 mm is just this distance, even lesser than this, and it's about less than 1/3 part. And now, formula for nth bright fringe is n capital D, distance of screen, and then distance between the sources. Now, fourth bright fringe, n is equal to 4 for fourth bright fringe. So y4 is 4 lambda d by d. And now from central fringe, from y4, now this y4 is the distance from the central fringe. See this. This is the distance. In our diagram, this is y4, which has been represented here as x. This y4 is from the center of the central fringe. So we just need to find out y4. And now, next problem. Young's double slit experiment using monochromatic light of wavelength lambda. The intensity of light at a point on the screen where path difference is lambda is k unit. What is the intensity of light at a point where the path difference is lambda by 3? And now this is the problem left to you. And kindly solve this problem and put it in comments. And the very first solution will be rewarded with suitable comments. And I will not be using directly this formula. I will be kindly try to use a modified form, and that is a quicker formula to solve this problem. With these words, I finish this lecture. In this lecture, we have solved NCERT for wave optics from problem number 1 to 4. And now, here is a challenging problem for you. Kindly post the solution of this problem number 5th. And if you like this video, then kindly share it. If you don't like, then comment on it about the negative points so that we can improve in future. With these words, thank you very much. And keep on watching my videos.